All right, so in C, we've got our basic building blocks, right? Integers, floats, characters. They're great. But what happens when you need something more? Something that actually represents a real-world object? Well, today, we're going to unlock one of C's absolute superpowers, building your own custom data types right from scratch. Let's get into it. So let's just start with a really practical problem. Picture this. You're building some software for a library, and you need to represent a book. Simple enough, right? But how do you actually store all the different pieces of information about one single book inside your code? Well, a book isn't just one single piece of data, is it? It's a whole collection of things. You've got the title, which is a string, the author, another string, the page count, that's a whole number, an integer, and then the price, which is a decimal, a float. C's basic types are fantastic for each of these individually, but what we really need is a way to bundle them all together to represent one thing, the book itself. And the answer to that problem, the tool that lets us do this, is the mighty structure, or as you'll see it in code, Struct. This is going to be our go-to for building complex, meaningful data types out of all those simpler pieces. So here's the official definition. A struct lets you group a bunch of logically related data items, like our book's title, author, and price, and give them a single convenient name. It's basically our way of telling the computer, hey, all these different variables, they belong together. They're all part of one bigger idea. And you know what? The syntax for this is actually pretty straightforward. You just start with the keyword struct, give your new data type a name, and then inside a pair of curly braces, you list out all the member variables that make it up. Oh, and you can't forget that little semicolon at the end. It's a classic C thing to forget, so watch out for it. Let's look at another classic example, a student struct. See how we've combined a character array for the student's name, an integer for their roll number, and a float for their CPI? Just like that, we've created a custom blueprint for what a student actually looks like in our program. Okay, so we've got a blueprint, but a blueprint for a house isn't a house, right? We need to actually use our new type to create a variable and store some real data. Let's see how we do that. It's really just like creating any other variable. You know how you'd write int x to make an integer? Well, now you just write struct student student1 to make a variable of our new student type. Boom, we've just brought our student blueprint to life. So how do we get data into our new student variable? For that, we use the dot operator. Seriously, just think of the dot as the key that lets you get inside the structure. When you write student1.cpi, you're basically saying, for this student1 variable, I want to access its CPI member. Then you can assign a value to it, just like you would with any other variable. Now, the struct is fantastic. You are going to use it all the time. But C has another kind of weird specialized tool for a very specific problem. Imagine you're programming for, say, a tiny microcontroller, where memory is incredibly scarce. In those situations, where every single byte counts, there's another option called the union. A union looks a lot like a struct, but it has one crucial, almost mind-bending difference. All of its members share the exact same spot in memory. What does that mean? It means you can only use one member at a time. It's a major trade-off. You save a ton of memory, but you can't store multiple values at once. Okay, let's watch this play out, because it's a little strange. We'll create a union variable and assign an integer, 456, to its roll no member. We print it out, and we get 456. Everything looks perfectly normal. So far, so good. All right, now the very next thing we do is use that same union variable, but this time we assign a float, 8.9, to the CPI member. We print the CPI, and again, it works just fine. We see 8.90 on the screen, no problem. But hang on a second. Think about it. That memory location was just holding our integer, 456. Now it's holding a float, 8.9. What do you think happened to that original roll number? Where did it go? And there's the catch. When we try to access roll no again, we don't get 456. We get garbage. The bits and bytes that used to represent our integer have been completely overwritten, steamrolled really, by the bits and bytes that represent the new float. They can't both exist in the same memory space. This strange behavior is the absolute fundamental difference between these two tools. So let's put them side by side, a final showdown, just to make it crystal clear when you should be using each one. This table really lays out the core trade-offs perfectly. With the struct, every single member gets its own private space in memory. So its total size is the sum of all its parts, and of course it can hold all those values at once. With a union, everyone shares one single space. Its size is only as big as its single largest member, but you can only store one value at a time. It's a choice between space and versatility.
Here's maybe the best way to think about it. A struct is like a filing cabinet. It's got a bunch of different labeled drawers, one for your name, one for your roll number, one for your CPI, and you can open any of them and get the data whenever you want. A union? That's like a single reusable drawer. You can put your files in it, sure, but if you then decide you need to store your tools in it, you have to take the files out first. You can't have both.
So what's the big takeaway here? It's actually pretty simple. 99% of the time, you're going to want to use a struct. It's the standard, powerful, and intuitive tool for grouping related data. You should really only reach for a union in those special, rare cases where memory is extremely tight and you know for a fact that you'll only ever need to store one of a few possible values at any given moment. And there you have it. You now have the power to go way beyond C's built-in types and create data structures that perfectly model whatever real-world problem you're trying to solve. Whether that's a book, a student, a car, maybe a pixel on a screen, the possibilities are literally endless. So the only question left is, what are you going to build first? Thanks for joining this explainer.